Hi, my name's Dan Bennett. I'm now a postdoc researcher at Aalto University in Elisa Meckler's ARIS group, but I did this work at Bristol University with Oussama Metatla and Roudaut. So I'm going to talk about our paper, Multifractal Mice. So at a high level, this is a paper about inferring features of user behavior and experience from mouse movement. In particular, we focus on one account of behavior and experience, readiness-to-hand. This is a construct from philosophy, which has been influential in HCI and design to understand fluid and engaged tool use. So what is readiness-to-hand? This is an idea drawn from philosophical phenomenology, though in HCI it has been mostly treated pragmatically, as a description of experience and behavior. From a pragmatic point of view, the story can be summarized as follows. When using a well-functioning tool skillfully, you stop being aware of the tool as a distinct object. You perceive through it to the task. Here, the tool is said to be ready to hand for the user. But this situation can break down, for instance if you're unskilled, or if the tool malfunctions, or if you're quite distracted. Then the tool becomes an object of conscious awareness. You detach from the task, and your attitude becomes more reflective and less tied to the original task content. For our purposes, we'll refer to this as not ready to hand. Now, I think it's clear why this might have been interesting for some HCI researchers. It gives descriptions of two quite different situations where users' patterns of attention, style of cognition, and manner of engagement are expected to differ in more or less predictable ways. Generally, ready-to-hand engagement has often been treated as a prototype of fluid technology use, good user experience, and good feel when controlling objects in a computer game. Researchers have also had ideas about non-ready-to-hand tool use, though these have been less consistent. Some accounts suggest that this is a state to be avoided and a marker of bad experience. Other accounts suggest that there are benefits to non-ready-to-hand states. For example, movement between these two modes might play an important role in creativity, observation, reflectiveness, learning, technology appropriation. Now, I think all of this raises a number of questions. First, do these states actually occur as described in a predictable way? And if they do, can we infer them from behavior? What kinds of outcomes do they support? Is the phenomenon reliable across different contexts? Are there really two cleanly divided modes here, or is it more of a spectrum? All of these questions will require empirical investigation, ideally guided by some theory of how the phenomenon arises. But to date, HCI hasn't had many options here. The one previous effort focused only on the relationship between attention and immersion and relied on distracting secondary measurement tasks. However, recent research in cognitive science offered us a way forwards. We built on work by Roudaut and colleagues which associated the phenomenon of ready-to-hand tool use with complex signatures in task-directed movement. They argue that ready-to-hand tool use arises due to a kind of complex sensory motor coupling with the tool, a cascade structure, which is known to give rise to signatures of multifractal nesting in movement. These signatures arise due to the coordination of a wide range of subprocesses. These cascade structures are known to support flexible adaptation in natural systems, and there is evidence of their role in human behavior. Roudaut and colleagues hypothesized that they played an important role in ready-to-hand tool use, supporting flexible engagement, and they argued that to maintain these states, conscious attentional resources are deprioritized, resulting in the tool's disappearance. Now, they tested these ideas using a game task and found that multifractal signatures in the mouse control hand were strong during normal play, and at the same time, players had low awareness of the tool, as measured by a visual awareness test. When the mouse was artificially broken during play, by distorting the relationship between mouse and cursor, multifractal signatures diminished, indicating reduced coupling. At the same time, awareness of the tool increased. Now, this was our starting point. We began by replicating, repeating the original experiment, but adapting the methodology to address issues relevant to HCI. We removed certain tasks that seemed unecological in a HCI context, and we refined the measurement of the user's locus of attention. Our results confirmed those of Roudaut et al. So then we extended their approach further. Roudaut et al. Had only focused on tool breakdown, which is only one aspect of readiness-to-hand. We drew out other hypotheses about readiness-to-hand and multifractality, concerning how 1. Learning and 2. Engagement affect the multifractal signature. Since ready-to-hand tool use relies on skill, we expected multifractality to be lower for the unfamiliar task, and higher as familiarity with the task increased over repeated play. To test this, we had players who had never played the game before repeatedly play the game without simulated breakdown. You can see here that multifractal signatures were significantly higher during the last game than during the first play. I said earlier that readiness to hand is associated with immersion and engagement, and previous work indicated that multifractal signatures in movement differed depending on how much a task relied on executive function. This is a construct somewhat related to engagement. As such, we predicted that multifractal signatures would be higher during a more engaging version of the task. To test this, we adapted the game to create a more engaging and motivating version. We introduced a mechanism that automatically matched difficulty to player skill, to provide a constant, manageable but increasing challenge. And we gave users feedback on progression through the levels of difficulty. We first validated this task to check that it was perceived as significantly more engaging, then compared repeated play under both versions of the game. Players in the more engaging condition showed significantly higher multifractal signatures from the start. So we tested these hypotheses using adaptations of the same game task used by Roudaut et al. In all cases, evidence supported our hypotheses. Multifractal signatures tracked 3 distinct dimensions of readiness to hand, predicting attention during breakdown, task familiarity, and the engagingness of the task. So what does this tell us, and where can we go from here? First, this provides further evidence for the theory that phenomena associated with readiness to hand have their basis in complex sensory-motor coupling between user and task environment. This in turn provides a source of testable hypotheses about further aspects of readiness to hand, allowing us to test and refine HCI researchers' ideas about the account. We discuss a range of issues and questions which need to be addressed to progress this. More immediately, our results point to multifractality as a nice feature which we can add to our toolkit to infer experience and behaviour. It's easy to capture, it relies only on the measurement of task-directed movement, and multifractality has been observed in a wide range of movement phenomena, making this likely to generalise. From a technical point of view, multifractality summarises non-ergodic, non-linear features of movement, making these features accessible to modelling and statistical approaches which are linear and non-dynamical. Our paper and supplementary materials introduce multifractal analysis for HCI researchers, and we provide scripts and guidance on parameter tuning. So I want to finish by thanking a lot of people who helped with this, whether by helping us to understand this methodology or how to explain it, named on the screen here. Finally, this work was supported by my ESPRC doctoral fellowship. Thank you.